Today's topic is relations and functions. So I like to think of functions as an input and output box. Something comes into the function, which is kind of like this magical lever box, and that generates an output. For instance, say that we have our classic y equals x. You put in an x value, such as 2, into the box, and the box gives you the same value, which is a 2. Or say that we're dealing with a relationship like y equals x squared. You plug in a 3 into the box, and it gives you a 9. So this idea of relationships defines a function because each x has to give a unique output value. So let's consider a set of points. Say that we have 4 separate points, like 1, 2, 1, 4, 2, 2, and 3, 4. So we can visualize this concept through a technique called mapping. So in this circle, we're going to have all of our x coordinates, or inputs, and in this circle, we're going to have all of our outputs. So here I'll label it inputs and outputs. So let's only list our inputs one time. We have our 1, which relates to the 2. We have our 2, which relates to the 2. And our 3, which relates to the 4. Now we're going to list our x values. So we're going to have our 2, our 4, our 2 again, and the 4 we already counted for. So here's when we have kind of a problem. Our box here says that whenever you plug in a 1, you get a 2 out. But in this case, it also says that whenever you plug in a 1, you get a 4 out. So how could that be? You can draw an arrow representing to each one, but it means that there's not a unique code here that relates each individual x value to an original y value. So in this case, this would not be a function. Well, it's okay that some of the y values repeat, because say that this 2 also links to a 2, you could draw an arrow here. This 2 doesn't have a relationship to any other number in the output, and this 3 relates to this 4. So once again, it's perfectly okay for it to have this unique relationship. So the way that you can tell from this mapping diagram whether or not something is a function is if an input has more than one arrow going into an output. So once again, it's okay if 2 arrows converge at the same output, we just can't repeat it from the same input. So let's try this again, now doing it with values that would represent a function. Let's say that we have the points of a classic slope-intercept line, like y equals 2x plus 1. So say that we plugged in a 1 for x, we would have 1, 3. A 2, we would have 2, 5. And a 3, we would have 3, 7. So whenever we put these values into a mapping, we should have a representation where every single input value has a unique output value. So let's try it out. We have 1, 2, and 3, and our output values are 3, 5, and 7. So let's see. Our 1 does have a unique arrow going to the 3. Our 2 does have a unique output going to our 5. And the 3 also has a unique output arrow going to a 7. So this function does represent a unique relationship where every single input can be related to a distinct output. Another way that this can be visualized is through the vertical line test. So this one is done through graphing. Let's kind of imagine some classic graphing relationships that we know, like just a line that we were just talking about. Y equals 2x plus 1. That would look something like this. So if we were to draw a vertical line, there's no place where it passes through the line in more than one location. So in this case, the function would pass the vertical line test, and it would be a function. But say that we considered another function like y equals the square root of x. In this case, or more precisely, y equals plus or minus the square root of x. In this case, there would be several locations that the vertical line would pass through the function. Because if we look at it like this, in this way, the vertical line would dissect and intersect the line in 2 points, here and here. So this function would not be considered a real functional relationship because each x input does not have a distinct output. So another way that we can also think about this is back to our slope days. So say that you had a horizontal line like y equals 3. So let's graph it out. It would look like this at the 3 value on the vertical y scale. So the slope for this line would be 0. And we're able to write it in slope-intercept form because we could say y equals 3x. Oh, my bad. Y would be 0x plus 3, which is simplified to y equals 3. And that does work as a function. However, if we had a vertical line, like something like this, going through the point 2, 0, the line function would be x equals 2, and its slope would be undefined. And there's no way that we could possibly put this into y-intercept form. So that's another demonstration that it's not a function. So relations and functions may seem to be building blocks off of previous concepts in algebra, but they also represent a fundamental way of thinking about numbers. It's kind of like mapping, where it's not just the x and y coordinate system, it's special systems in which coordinates are related to each other. Going back to our original sets of points, say like 1, 4, and 2, 3, and 1, 5. The boundaries of this relationship only exist from these 3 points. We can't define this function based on any other input value, so we only have to go off of what it gives us. And because of the fact that the 1 can be taken to the 4, but also to the 5, we can say that this is not a true functional relationship because the distinct inputs don't correspond to the distinct outputs. So this way, it has an easy definition of what is a functional relationship. So please like the video and subscribe to our channel. All support is appreciated. If you have any questions or feedback, we would love that to help make these videos better. Thank you.